Okay, so we can start our meeting from section A. So section A has 30 multiple choice questions. You can see them there. So we'll be answering them, and this I'll be also explaining the concepts behind so that we get to understand what we're doing. Okay, so if you have any questions, please feel free to ask. Okay, so the first question here, they're saying, uh, what is the state when an electron in a hydrogen atom is in N2? Okay, so what is the state when an electron in a hydrogen atom is in N2? So anyone who can help us with the answer there. What do you think? What should be the answer there? If it's in N2, and then that electron is in the hydrogen atom, okay? Would be that state would be called a stable state, would be called a ground state, would be called an excited state, or it's actually none of the above. So anyone who can help us with that question? What do you think?
Good evening, sir.
Good evening.
Okay, I think it will be in the excited state.
Should be in the excited state. Okay, thank you for that. Anyone else? Anyone else? Okay, so whatever she said, that's the correct answer. Okay, so if the electron is in any other state apart from the ground state, then we're going to say that that electron is in the excited state. So the ground state is when n is equals to 1. Okay, so any n that is higher than 1 might be in N3, N4, whatever n is higher than this N1, okay, it will mean that that electron is in the excited state. So here we'll pick, which one is this? We'll pick C there as our answer. Okay, so number 2, they're saying each small packet of energy or discrete unit is called, okay, each small packet of energy or discrete unit is called. So this is what we call as the quantum. Okay, so the quantum is just a small packet of energy or discrete unit. Okay, so we pick C here as the best answer. And then those others, they are self-explanatory. Radiation is not a small packet of energy. Frequency is not even energy. It's a measure of something there. Okay, so we're going to pick quantum there as our answer on number 2. And then number 3, they're saying the energy of a photon is given by the formula energy is equals to the Planck's constant multiplied by this thing here that looks like a V. Okay, so this V, what is the V in this equation? So this V here represents the frequency. Okay, so V represents the frequency. Okay, so when we come to the options here, okay, the options here, there's the Broglie's constant, there's Planck's constant, there's Rebec's constant, and then there's none of the above. So here we're going to pick none of the above, okay? Because this V here represents the frequency, and we can't see it here on the options. So pick none of the above there. So if you have any questions, please ask. Otherwise, I'll move to the other question, which is question 4 now. So on question 4, they're saying, choose the correct statement. Okay, so A, they're saying pure liquids and aqueous solutions are not included in chemical equilibrium expressions. Okay, so this one is false because aqueous solutions are included, okay, in the chemical equilibrium expressions. And then pure liquids or pure solids. So pure liquids or pure solids are the ones that are not included. So this one, since it said pure liquids is included here, we're going to say it's false. And then here they're saying pure solids and pure gases are not included. Okay, so these gases here, the gases are included in the chemical equilibrium expressions. Okay, so see, they're saying what? So this one also becomes false because they're saying the gases are not included, but the gases are included. And then C, pure solids and aqueous solutions are not included. Okay, so the aqueous are included, but the pure solids are the ones that are not included. So even this one is false. So here we're going to choose option 4. I mean option D, which is none of the above. Okay, so to get the concept here, I said the pure solids and the pure liquids. When you're finding the equilibrium constant, okay, you do not include them. Okay, you do not include them in the what? In the expression. You don't include them. You always include aqueous solutions and the gases. They're the ones that you include there when you're finding the um, equilibrium constant. Okay, so here we are going to choose D. Okay, and then we can move to question 5. So question 5 now they're saying how many orbitals are in the principal quantum number 4? Okay, how many uh, orbitals are in the principal quantum number 4? So here I'll show you the general thing that you need to do in case they bring another quantum number there. Okay, so if your n is 1, then you can only have one s subshell. Okay, if your n is 2, n2 like that, then you can have 2s and 2p. If your n is 3, then you can have 3s, 3p, and then 3d. If your n is 4, okay, you're going to have 4s, 4p, and then 4d, and then 4f, like that. Okay, so now the subshell S has one orbital. Okay, the subshell P has it has 3 orbitals, and then D has 5, and then F has 7. So here, if my N is 4, then I'll have these subshells, right? So it means here, since I have the S subshell here, I'm going to have one orbital there. And then here I have the P orbital, I mean the P subshell. So the P subshell has 3 orbitals. The D subshell has 5, and then this one here, which is the F subshell, has 7. Okay, so they increase by 2 like that. So if we had a G somewhere there, it will have 9. Okay, so we can now add these things here. So if we add this, it will be 1 plus 3, that is 4. 4 plus 5, that is 9. 9 plus this, that will give me what? 16. So if my N is 4, okay, I should have 16 orbitals. But I see that on these options here, I do not have it. So I choose none of the above as my answer. Okay. And then there's also a short form for finding how many orbitals you have. So you can say n to the power 2. So that would be 4 squared, okay, which will just be 16, like that. But this one here is the best because it will show you individually. Because oh yeah, so it will show you individually there how many orbitals are there. Okay, so you can see if I'm here, I only have this one, right? If my n is 1, then I'll do 1 squared. It will give me 1 orbital. So here I only have 1 orbital. If my n is 2, it will be 2 to the power 2. I'll have 4 orbitals. So those 4 orbitals come from 1 from here and then 3 from the p. So they give me 4. Okay? And then if I have 3 squared, this one here will give me what? 9. So if I come here I have 1 because this is S. And then in the P, I have 3. So I have 1 plus 3, that is 4. And then in the D, I always have 5 orbitals. So when I add them, um, I get 9. Okay, so I just explained that for you to get the concept. But if you forget whatever I was doing, just say that the number of orbitals are equals to n squared, where n is the principal quantum number. then you get the answer easily. So there we see that there's no answer there. There's no 16. So we choose none of the above. Okay. So we move unless there are questions. So I'll only stop when you have a question. So here, number 6, they're saying when n is equals to 3, which quantum number indicated below is not permitted? Okay, so remember we have the principal quantum number, which is represented by n. We have the angular momentum quantum number, which is represented by L. We have the magnetic quantum number, which is represented by ML. And then we have the spin quantum number, which is represented by MS, like this. Okay, so depending on the value of n that you have, you can know all these other quantum numbers. Okay, so the principal quantum number n, okay, and then the L here, which is the angular momentum quantum number, will go from 1 all the way to n minus 1. Okay, and then the magnetic quantum number goes from minus L, and then somewhere here it will be 0, and then it goes to positive L like this. Okay, and then this spin quantum number, it only has two values. It's either it's positive half if the electron is facing up like this, or it is minus half if the electron is facing down. So let's put 3 here. So if I have 3 here, okay, then I expect that my angular momentum quantum number should be 1 and 2. Okay, because we said 1 to n minus 2. So this is the 1, and then n minus 2, it will be 3 minus 1, which is 2. So I can only have these two. So let me write them in this way. I can have 1 and 2 as my angular momentum quantum number. So for this one here, I'll have minus 1 because this is my L now. And then I'll have 0 somewhere, and then positive 1. And then this one, I'll have minus 2, minus 1, 0, plus 1, and then plus 2. Okay, and then here now I will just have for the electrons that are here, I'll have plus half minus half. Even this one here, plus half minus half. It just depends on the direction where the electron is facing, even here. So here, when I come here, they're saying which quantum number indicated below is not permitted. So L is equals to 2 plus. We see that it's one of them, so it's permitted. Okay. Um, ah, oh, L is 2 plus. It's this one here, not that one that I said. It's this one here. So L being 2 plus, it's permitted. It's this one here. Okay. Then MLB minus 1, we can see we have a minus 1 there, minus 1. And then MS here, which is the magnetic quantum number, is minus 2. But we said this, not magnetic quantum number, I mean, but the spin, we said the spin can only be positive half or minus half. So this minus 2 cannot be permitted. So we choose C as the best option there for the one that is not what? Permitted. Okay. So now we move to question 7. Okay, so question 7, they're saying what? They're saying what is the electron configuration of for silicon, which has atomic number 14. Okay, so when writing this electronic configuration, always write this. So you write 1s, okay, and then you write 2s, 2p, 3s, 3p, 3d. Okay, I can see there's no 3D there. So it means this will be enough. So now we're going to fill in these orbitals in this way. We're going to move like this. And then like that. Okay, so we know that the S can only contain 2 electrons because it only has 1 orbital. So each orbital contains a maximum of 2 electrons. So here I have 14 electrons to distribute. Okay, so here in the first 1s, I'm going to have 2. And then I go to the 2s. Okay, since it's 2s, the maximum that it can hold is 2. And then I go to the 2p because I'm following this car R, where it's coming from like that. So that's where I'm starting. So from here, the 2s, I go where it's starting from there. So it will be 2p. And we know that in the p, there are 3 orbitals. So each of those orbitals can hold the 2 electrons. So since there are 3, it will be able to hold the 6. So here I'm going to put 6. And then from there, I go to the 3s. Okay. Since this is S, it can only odd 2. Okay, so now you can count. So this is 4, and then plus 6, 10, and then this one, 12. So I'm only remaining with the 2 from this 14 here. Okay, so these two, they'll come in here, the 3p. So I write 3p here, then I write 2. So I'm looking for this electronic configuration on the options that have been given. Okay, so which one is it? Which one is it? Okay, so if I look at A, I have one S has 2, and then 2p has 6. So this one is the force. Okay, and then these ones here, okay, let me look at P. 1S has 2, 2S has 2, 2P has 6, 3S has 2, 3P has 2. Okay, this one is okay. And then what about this one? 1S2, 2S2, 2P3, 2, and then okay, so this one here is wrong because they have started with the 3P here before the 3S. Okay, but according to this diagram, we first meet 3S and then 3P. So even this one is wrong. So if you don't know this card diagram here, then you'll be gone here. Okay, so know this card diagram. I think we had similar questions in the assignments where I was doing such a thing. Okay, so you can watch that video to understand more. But if you have any questions, you can ask even right here. Okay, so the best answer there that we're picking is what? Option B, this one here. That's the best answer that we are picking. Any questions there? Okay.
Good evening, sir.
Oh, all right. If there's a question you can ask.
I'm a bit behind on how you got the 2p6,
Oh, now I got the what?
the 2p6.
Oh, okay, I've seen. So you're saying you're behind on how I got this one here,
Yes, sir.
right? Okay. So here it's just the matter of the type of subshell that you're dealing with. So we said in the S here, in the S, there is one orbital. Okay, so this one orbital can hold a maximum of 2 electrons. So no wonder you can see wherever there's S here, we are putting a maximum of 2 electrons. Okay, and then if you have the P subshell has 3 orbitals. So each of these 3 orbitals can hold 2 electrons. Okay, so in the first one, 2, in the second one, 2, in the third one, 2. So it means that in this p subshell, we're going to have what? 6 electrons like this. So this is the 6 that you are seeing here. Okay. But why didn't we put 6 as well here? Because the electrons that we are distributing have finished. Okay. So we are following this. The first one we put 2 because it's the S. The second one we put 2 as well because it's the S. And then when we start from here, we start from the 2p. So we've just put 2 electrons here, 2 electrons here. So I'm remaining with 10. So it means there in the 2p, I can put 6. I put 6 there. And then 3s, I put 2. So when I count from here up to where I started from here, those are 12 electrons. So from 14, I'm remaining with 12. So the remaining ones, I put them in the next uh, subshell. Okay, I put them in the next subshell. So the next subshell is 3p. We know that 3p can hold up to 6, but we're only remaining with 2. So we put the remaining 2 there. No wonder here and there they're different because here there's just remaining 2. Okay, so that's why we put 6 there because the p subshell has 3 orbitals and each of those 3 orbitals can hold up to 2 electrons. No wonder we're putting 6 there.
Okay, sir. Thank you.
Okay. Okay, so and then question number 9, this one is very simple. It's just a definition. So question number 9, they're saying what? Oh, did we solve question number 8? No, didn't solve question number 8. So let's look at question number 8 first of all. So question number 8, they're saying which set of quantum numbers corresponds to the 6th electron in this silicon? Okay, so remember we said the correct electronic configuration was this one, right? So we want to find the set of 4 quantum numbers that would describe the electron, that would describe the 6th electron in that atom. Okay, so now I'll be drawing these subshells. Okay, so in 1s, I only have one orbital, so I draw it like this. So this is my 1s. So I have 2 orbitals there, so I'll put one facing up, the other one facing down. And then in 2s, okay, in 2s, I'll put again 2 electrons, one facing up, the other one facing down. So this is 2s. And then now in 2p6 there, okay, since that one is the p subshell, it has 3 orbitals. So I separate this guy into 3 like this. So this is my 2p. And then I know that it has 6 electrons. So I have 1 there, 2, 3, 4, 5, and then 6. Okay, so if I start counting, which one is my 6th electron? These 2 arrows represents the electron. So this is my first one, second, 3, 4, 5, 6. So you see that the 6th electron is this one here, and it's facing down. Okay, so since it's facing down, then we definitely know that the spin will be -1/2 because it's facing down. Okay, and then it's in the 2p subshell. So the 2p subshell, this 2 in front here indicates the principal quantum number. So it means my n there will just be 2. And then it's in the p subshell. The p subshell simply means that L is equals to 1. Okay? The p subshell simply means that L is equals to what? To 1. Okay. And then what else should we find? So this here was the ms, the spin. Since it's facing down, we are getting it as a -1/2. And then what is remaining is the ml. Okay, so the ml, how do we find it? Okay, so remember we said if we have L, then this ml will go from -L in the middle somewhere to meet 0, and then to go to positive L. Okay, so since my L is 1, because this is P subshell, okay, it means that my ml, okay, will have -1, 0, and +1. So this -1 is for this first box here. So this is -1. Okay. And then the second one is this one with the 0. And then the third one is this one with the +1. So it means there, where is this 6th electron? We are seeing it is in the -1. So the L there has to be what? Has to be -1. Okay, the ml has to be -1 because I'm saying -1, 0, 1. Okay, so if you can look at this here, where do we have that set? Where my n is 2, L is 1, ml is equals to -1, and then ms is equals to -1/2. Where is this set here? Okay, on our options. So I think A satisfies it because you can see N is 2, L is 1, and then ML is what? ML is -1, which is what I found there. Okay, and then MS is -1/2 because this guy here is facing down like this. Okay, so we're going to choose this one here as our best answer. So I've shown how to find all those 4 quantum numbers. Okay, and then question number 9, they're saying, what is a Lewis acid? Okay, what is a Lewis acid? So this is just a definition. Okay, so if you're defining the acids and the bases using Lewis's theory, you're going to say an acid is an electron acceptor. Okay, an acid is an electron acceptor. So we choose B there. So B, that's the correct answer there. Okay, and then we can move up to question number 10. Okay, so question number 10, they're saying, what term is used to describe orbitals with the same energy? Okay, what term is used to describe orbitals with the same energy? So if the orbitals have the same energy, then they are called degenerate orbitals. So we choose the C there as the correct answer. Okay, and then what is the value of L in an orbital written as 4G3? So here you have to know this, okay? So if okay, if my if my L is 0, okay, then I have the S subshell. If my L is 1, I have the P. If my L is if my L is 2, I'll have the D. If my L is 3, I'll have the F. If my L is 4, I'll have the G. So here I can see the G subshell. Okay, I can see the G subshell. So meaning that my L there is simply 4. So I come here and pick 4. So make sure you memorize these guys. Okay, L0 S, 1 P, 2 D, 3 F, and then um, L4 is equals to G. Okay, so meaning that okay, we can continue going. If you write L5, that will just be H. Okay, just like that. So the answer there is C. And then 12, what is the principal quantum number in 5p2? So the principal quantum number is always the first number that you can see here. So it's 5. So you pick 5 there. Okay, pick 5 there. Unless there are questions. Okay, if there are no questions, I'll move to question number 13. So question number 13, they're saying which wavelength lines fall in the infrared region of the electromagnetic spectrum? Okay, so they've given us different series here. So the series are not hard. Okay, the series are not hard. So in the electron, okay, the electrons make what we call as energy transitions. So remember, if this is my nucleus here, okay, it contains the protons, the neutrons, and then I have these shells around this nucleus like this. Okay, and then let's say I have an electron somewhere here. So this electron is in N1. This is N1, this is N2, this is N3. Okay, so this electron here in N1, it can gain energy and then it will jump and will go to N3. Okay, so what it has done there, it has made an energy transition from a lower energy level N1 to a higher energy level N3. Okay, so it can also make the transition in the opposite direction. Maybe say it was here and then it has lost energy and then it goes to 1 here. Okay, so now there are different series that describes the final destination of this electron. Okay, so the electron can come from whatever energy level, but as long as the final energy level where it lands is equals to 1, that will be called the Lehman series. Okay, to be called the Lehman series. If my N final, okay, it's coming from wherever it's coming, maybe it's coming from N5 and then it ends up in N2. Okay, that gives us the Balmer series. The Balmer series, if N final is 3, that gives us what we call as the pass chain series. Okay, if N final is equals to 4, that gives us what we call as the bracket series. Okay, the bracket series. If my N final is 5, we have what we call as the P funds. So these are the ones that you're supposed to know. Okay, so an electron can come from wherever it can come from, but as long as it ends at 1, Lehman series, ends at 2, Balmer, ends at 3, pass chain, ends at 4, bracket, ends at 5, that's a P fund. So now, depending on where it ends, it will tell you the type of electromagnetic radiation that it has. Okay, so for the for the for the N1, okay, if it ends in N1, then the type of radiation that we have here will be ultraviolet. Ultraviolet radiation. Okay, if it goes and ends up in N1, okay, or it's when you're dealing with the Lehman series, the radiation there is ultraviolet. And then when you're dealing with the Balmer series, the radiation there is visible light. Okay. And then whatever comes after visible light is infrared. So all these wherever you can go down here, you're going to find infrared radiation. Okay, so here they're saying which wavelength lines fall in the infrared region here. Okay, so among these here, which one falls in the infrared? So they have put Raman. No, this is for ultraviolet. The Bauma is for the visible light. So the pass chain here is the one that is in what? The infrared. So starting from the pass chain, going down here to whatever you can go, the radiation will always be infrared radiation. So we pick F. Is it C there? We pick C as the best answer there. Okay. So this series I've emphasized even in the tutorial videos. You need to know them to easily answer the questions. Because if you don't know this series, then how are you going to answer this question? You cannot answer. Okay, unless you just guess and then you pray to God that you get the answer correct. Okay, so that is that about the series. So I'll erase this and then go to question 14. Okay, so question 14, they're saying, choose the correct statement about chemical equilibrium. Okay, so A, they're saying it's a static process. B, they're saying it's both static and dynamic process. C, they're saying it's a dynamic process. Okay, so the correct answer there is C. So chemical equilibrium is a dynamic process. So by dynamic process, what do we mean? We mean that the rate of the forward and the backward reaction are the same. Okay, so meaning the rate at which the reactants are forming products, okay, is the same as the rate at which the products are forming the reactants. Then we'll say that here there's dynamic equilibrium there. Okay, because the rate of forming the products and the rate of forming the reactants is the same. It doesn't mean that the amount of product and the amount of reactant is the same. No, it doesn't mean that. It means the rate, okay? So always it's about the rate and not the amount. The amount of reactant and product can be different, but the rate at which the reactants are forming the products and the products are forming back the reactants, it will be the same. So it will be in a dynamic equilibrium like that. Okay, so the correct answer here, we're going to choose C. Okay, what about question 15? Question 15, they're saying, which statement correctly describes the state at equilibrium? Okay, so at equilibrium, we expect that the reaction quotient, okay, the reaction quotient should be equal to the equilibrium constant. So the correct answer there is just C, okay? When these two are equal, then we'll be at what? Equilibrium. So this Q, okay, represents what we call as the reaction quotient, which is just the ratio of the products to the reactants, okay? Of course, based on their stoichiochemic moles. And then even the K, which represents the chemical, the equilibrium constant, I mean, it's also the product and the reactants at equilibrium, okay? So this one, the reaction quotient, can be the ratio of the product and the reactant at any time, okay, when that reaction is happening. But the equilibrium constant has to be the ratio of the product and the reactant at equilibrium and nowhere else. Okay, so if these two are equal, then it means that the reaction is what? That means that the reaction is at equilibrium. Okay, so we choose C there as the correct answer. And then 16, they're saying under chemical equilibrium, what does the letter Q represent? Oh, I've already said, okay, it represents the reaction quotient here, this one here. Okay, so that's that there. So if there are any questions, you can ask. Otherwise, I'll move to question 17. So I'll erase this. So question 17, they're saying, how many phases are in homogeneous equilibria? Okay, so just by the term homogeneous equilibria. So homogeneous equilibria, it means that all the species in the reaction that you're carrying out should be in one phase. So meaning that if they are solids, let them all be solids. If they are liquids, let them all be liquids. If they are gases, let them all be gases. That's what we mean by homogeneous. Okay? So in homogeneous equilibria, we only have one phase. Okay? So the answer here is B. So it's either you are reacting gases, maybe hydrogen, 5 hydrogen in gas, then the nitrogen should also be in gas. And whatever I'm going to produce, if it's ammonia, should also be in gas. That's what we mean by homogeneous. So there's only one phase because they are in the same states like that. Okay, so we choose B as the correct answer there. Okay, so the other question there is question 18. They're saying when Q, which is the reaction quotient, is greater than K, okay, what happens to the reaction? Okay, what happens to the reaction? So remember, we said Q is the ratio of the products to the reactants at any time. Okay, at any time. And then K is the ratio of the products and the reactants at equilibrium. Okay, so when this Q, okay, when this Q is greater than K, what does it mean? Okay, when this Q is greater than K, what does it mean? When the Q is greater than K, okay, it simply means that it simply means that we have more okay, so when Q is greater than K, simply means that the ratio of the products to the reactant is too high. So meaning that we have more products, okay, in the reaction. So for this guy here to be greater, it means we have a lot of the products and the reactants are at a very low number. So for example, Q, maybe the product is at 100, and then let's say the reactants are at 2. So this will give you like 50, which will be greater than the K that is at equilibrium. So if Q is greater than K, then it means we have more products, okay, in the reaction. So if you have more products, then what will happen to the reaction according to the Chatrias principle? It will shift to the left so that it reduces the amount of product and it produces more of the what? Of the reactants. So here, which one agrees with whatever I've said? They're saying the equilibrium shifts to the left. Okay, this is true towards the reactants. Okay, so because there will be more products in that reaction, no wonder the Q is greater. So in another scenario, it's not here, but they may ask you if the Q is less than K. Here, it simply means we have more reactants. Okay, so what will happen to the reaction? It will shift to the right so that it uses those more reactants that we have. Okay, it uses those. What is happening to my screen now? Okay, so that it uses those more reactions that we have, okay, to produce the products. Okay, so you should have that in mind. It can come. Okay, this question can come. It's a very common question. If Q is greater, then you know that it shifts to the left. If Q is less, it shifts to the right to produce more products. Okay, so here we choose B as the correct answer. And then on 19, they're saying what? Okay, on 19, they're saying, what is T? Okay, on 19, they're saying, what is T in this expression here? So this expression is the expression that we use to calculate to convert the equilibrium constant, okay, from the equilibrium constant based on concentrations to the equilibrium constant based on pressure. Okay, so this is the equilibrium concentration based on pressure, based on concentrations. The R is the universal gas constant. The T there represents the temperature in kelvins. Okay, temperature in kelvins. But you can see that from our options here, we do not have any kelvins. Okay, so we are going to say none of the above choices. So we pick D as the best answer there. Okay, what about question 20? So question 20, what are they saying? They're saying determine the value of change in N in the reaction below. Okay, so what is change in N? Or they write like a triangle and then N. So that means change in N. So change in N, okay, it's the difference between the moles of gaseous products and the moles of gaseous reactants. So in this reaction here, we're first going to look at it. The first thing is to see if it's balanced. So I can see 1 calcium, 3 oxygen, 3 oxygens, 1 sulfur, 1 sulfur. So it's balanced, okay? And then now we said this N here is the difference because between the moles, um, the the gaseous moles of the products, okay, minus the gaseous moles of the reactants. So when I come to the product here, am I seeing any gas on the side of the products? No. So it means the gaseous moles on the product side here is just 0. And then minus, when I come to the reactants, am I seeing any gas? Yes, I can see this gas. So you get the coefficient in front here. So the coefficient here in front of this sulfur dioxide is just 1. So I'll write 1 there. So it means here, okay, this one just give me -1. So is there a -1 here? We see that it's not there. So the answer there is none of the above. Okay, so that's the correct answer there. And then 21, predicting the effect of change in concentration on equilibrium position. Okay, so I've been given this equation. Okay, I'm very sure it's balanced because I can see a 2 there, a 2 there. So this one is balanced definitely. Okay, so they're saying, so here we are using Le Chatelier's principle. Okay, so they're saying what happens to the concentration of oxygen here, which is a reactant, if water is increased. Okay, so if they increase water here, what will the reaction do? Okay, so according to Le Chatelier's principle, if the products are increased, then they will be reacting more, okay, so that they can produce more reactant. So if I add more water here, which is a product, it will be reacting with this thing that is here to produce more of the oxygen. Okay, so it means that the concentration of the oxygen is going to do what? It's going to increase. Okay, the concentration of the oxygen is going to increase there. Why? Because we have increased this water here. Okay, so the reaction as it is fighting to bring about the stability that it had, okay, it will produce more of the oxygen. So we are going to pick C there as our best answer. Okay, what about question 22? It's also based on the same reaction. They're saying what happens if H2S, what happens to H2S if oxygen is added? So if I add more oxygen here, it means I've added I've added more reactant, right? So it means the reaction on this left-hand side, okay, is going to increase. So if the reaction increases, then the concentration of this guy is going to do what? It's going to go down because they'll be producing more of the products. So the concentration of this guy is going to reduce. So we pick B there as the best answer there. Okay, and then which model defines acids and bases in terms of protons? Okay, so the model that does that is the Bronsted Rowe model. Okay, so this one here, the Lewis model is based on electrons. Okay, based on electrons. The Arrhenius is based on the hydrogen ion, okay, and then this one here is based on the protons. So that's how they move there. So make sure you know them. So if you are talking about Arrhenius model, you're talking about hydrogen ions. Lewis model, you're talking about electrons. And then the Bronsted-Rowe model, you're talking about the what? The protons. So make sure you know them in that way. Okay. All right. So 24, what are they saying on 24? So these are similar questions to what you had in the tutorial sheet, this 24 here. So they're just saying, choose the conjugate base for the Bronsted acid, this one. So they've given me the acid. They want me to choose the conjugate what? Base. So we said the conjugate base, okay, forms when the acid, okay, the conjugate base forms when the acid loses one proton. So that proton that we mean is the hydrogen. So this guy here, been given HPO4 2-. Okay, so if this guy loses one of this hydrogen, then what do you think is going to form? So the hydrogen, when it leaves here, okay, is going to go with a positive charge. So if this was -2 with a positive charge present, okay, when it leaves, it means this hydrogen will leave, so it will be PO4 4, and then this charge here, since the one proton has gone, or one positive charge has gone, it will become -3 like this. So this one here is the conjugate base for this Bronsted acid here. But when I come on my options, I do not see it. Okay, I do not see any of it. So I'm going to choose none of the above there. Okay, so remember, the conjugate base is obtained from the acid by removing one hydrogen. Okay, so it is true for the opposite. So meaning that the conjugate acid for the Bronsted base is obtained by adding one electron to that base. I mean by adding one hydrogen to that base. Okay, so that is the next question there. So look at this question here, question number 25. They're saying the conjugate acid for this base would be, so this is the base. So for me to get the conjugate acid, I need to add a hydrogen there. Okay, so a hydrogen ion. Sorry, hydrogen ion plus HSO4 minus. Okay, so this positive and the negative, they cancel out. And then H plus H, I get what? H2SO4, like this. So when I come here, I cannot find it anywhere. So I'm also going to choose none of the above there. None of the above choices. So that's the answer there. Okay, so any questions there? Okay, so if there are no questions, I'll proceed to question 26. So question 26, they're saying, which terminology describes solutions that are capable of resisting large change in pH upon addition of a strong acid or base? So these are buffers. So buffer solutions, okay, so that one is straightforward. And then here they're saying the pKb, okay, the pKb of a certain base is this at 25 degrees Celsius. What is the Kb value? Okay, so the formula for the pKb is pKb is equals to minus log, and then you put the concentration of the Kb here, like this. So that's the formula there. So now I've been given the pK value as this. I want to find the Kb value. So what do I do? So I can put it here. Okay, 5.72 is equals to, and then I can divide both sides by negative, so it will be minus, and then log, and then I have Kb there inside the brackets. So we know that when you just write log here, it means this is in base 10. Okay, so in math now, we learned how to change the log to the exponential. So this one has base 10. So we use what we call as BAM. So base to the power answer is equals to what is in the middle. So this is the base, okay, to the power answer is equals to what is in the middle. So I should write it in this form: log base 10, and then Kb is equals to minus 5 point, like that. So this is base to the power answer is equals to what is in the middle. So what is in the middle is the Kb. So I'm going to write the Kb is equals to base, which is 10 to the power answer minus 5.72. So just punch this now onto your calculator to see what you're going to get. Okay, so when I punch this on my calculator, I'm getting 1.905 times 10 to the power minus 6. Okay, so I can round this off to two decimal numbers. So it will just be 1.9 times 10 to the power minus 6. Okay, so is there any answer which looks like this on the options? Yes, so A. So we choose A there as our best answer. Okay, so we choose A there as our best answer. Okay, so that's the answer there. And then I can erase this. So on question number 28, okay, they're saying determine the value of Ka with reference to 27. So Kb, we found it was 1.9 times 10 to the power minus 6, right? And then they want us to find this Ka with reference to this. So what you have to know here is this equation for you to find this. Okay, you have to know that Ka multiplied by Kb at 25 degrees Celsius. This temperature here is very important. If it wasn't 25 degrees Celsius, we can't use this equation. Okay, so at 25 degrees Celsius, if I multiply my Ka and my Kb, I always get 1.0 times 10 to the power minus 14. Okay, so now here I have my Kb value. So my Ka will just be equals to, I divide both sides by Kb. So it will be 1.0 times 10 to the power minus 14 like this, divided by 1.9 times 10 to the power minus 6. So Ka will be equals to, so make sure you put these things in brackets as you are punching them on the calculator. So you open the brackets, you type this, you close, and then you say divided by, and then you open another bracket, you type this, and then you close, okay, and then you punch. So the value that you should give you there should be 5.3 times 10 to the power minus 9. So this is the answer there, okay? So is it there on the options? Yes, I can see it on B. So we choose B there as the correct answer. Okay, and then 29. So determine pKa at 25 degrees Celsius with reference to question 27. So we found that the Ka value was this, right? So the pKa is equals to minus log, and then you multiply with the Ka value. So pKa will be equals to minus log of the Ka value that we found. So 5.3 times 10 to the power minus 9 like this. So what we need is just to punch this value onto our calculator. Okay, so if you punch this onto our calculator, what do we get? So let me do it. Okay, so when I punch this, I'm getting approximately 8.28 like this. I round it off to 2 decimal places. So I'm going to pick C as my best answer there. That's how we find the pKa. Okay, and then question 30, they're saying, is a solution with the concentration of the OH being given as this, acidic, basic, or neutral? So we can only tell if we calculate the pH. So if the pH is equals to 7, that will be neutral. If it is less than 7, that will be acidic. If it's greater than 7, that will be basic. So how do we calculate the pH when we have been given the OH, the OH concentration? So what we are going to calculate here is the POH. Okay, POH should just be minus log, and then the concentration of the OH, which is 2.4 times 10 to the power minus 8. So you can punch this on your calculator, minus log, and then in brackets you put 2.4 times 10 to the power minus 8. Okay, let me do that on my calculator. Okay, so on my calculator, it gives me what now? Let me do this. Okay, so it's giving me about 7.6198. So counter check with your calculator. So this is my POH. Okay, so it turns out that pH plus POH should always be equals to what? 14. So it means my pH will just be equals to 14 minus POH. So 14 minus the POH, 7.6198. This will give me what now? Okay, it will give me approximately 6.3802. And we see that this pH is actually less than 7. So it means this solution will be what? Acidic. Okay, so I'm going to choose A there as my best answer. Okay, so any questions there? It means we are done with section A. We're done with section A. So we can now go to section B. But any questions from section A? Okay, so thank you so much for watching this video. If you'd like to access the full video solutions, okay, where I'll be solving the rest of the questions of test 2, meaning question 16 all the way up to 30, as well as section B, you are free to register with us. You can check the link in the description below. Okay, it's going to give you a link to our website, which is discretelearning.com, a link to our mobile app, okay, as well as a link to a video registration guide. So as you are revising for your exam, for your tests, you can find more helpful videos on our website. Okay, so let me show you the website. So when you go on the website, you'll find something like this. Okay, so we have a lot of courses that we offer here. So if you know anyone who is doing some of these courses, you are free to refer them to us. Okay, so all those who are doing biochemistry, anatomy, human physiology, immunology, and any other medical course that you know, okay, you can refer them to us, or those who are doing math courses. Okay, so here I want to show you what we have in this course called chemistry. So I'll open it, and then I'll go to general chemistry if you are semester 1 Apex or any other university. If you are semester 2 Apex, you go here. So semester 1, okay, you see that we have some folders there that have helpful information for you. So we have lessons and tutorials. So on each topic that you can think of in chemistry, we've solved and we've taught. Okay, on each and every topic that you want, you'll find the lessons there. Here, there are handwritten summarized notes. You can use them, okay, for your advantage. Very well summarized. Here, there are tutorial sheets and assignments. Okay, so all the tutorial sheets for this semester have been solved, and you can find them there. Okay, and as well for the past intakes. The past papers, you're going to find them there. So you can open it, and then you go to the part of the university that you belong. So Apex, you go to Apex. You're going to find video solutions here and as well as written solutions there. Okay, so you see that there are a lot of papers here. We have some exam papers, 2023 January, 2023 July, final exam. We have the quizzes, okay, we have the tests, 2024 July final exam. We have all these papers that can help you prepare for the exam. Okay, so if you like to join our ever-growing community, okay, you are very much welcome. Just check the link in the description below. It will help you register. Okay, so thank you so much. Until next time.